everybody. Welcome to the next session here. We have David Hewitt is going to be speaking on how Python harnesses Rust through PyO3. This is a 45-minute session. We may have time at the end for a few questions here, and if not, David has graciously volunteered to spend a little time outside, and you can maybe talk with him there. Say hi to David.
Good afternoon. Thank you very much for cutting your lunch a little short if you had to rush up here to come see me. I'm very excited to be here this afternoon to talk to you all about this topic. As the title says, I'm going to focus on how Python harnesses Rust through PyO3. And what am I trying to get at by that? Well, let's start with an observation. So you've probably noticed that Rust is increasing as a popularity as a language for implementing Python software. And what you might not know is what that actually means, how that's actually working. And what I want to do today is to try and illustrate that for you. And so we'll start by talking a little bit about Rust and a little bit about a library called PyO3 that's used to do all of this. Then we'll take a look at a Python function call, and we'll actually go down the rabbit hole and find our way to the Rust code. And finally, we'll wrap up. I want to give you a couple of key takeaways, and then, time permitting, we'll take a couple of questions. First, about me. So I've been a Python developer for about 10 years now, and I discovered Rust something like 8 years ago. I fell in love with both of these languages. Something like half of that, 5 years ago, I started contributing to an open source library called PyO3. In that time, I've become maybe the lead maintainer, you could call me. I've done the most work on it in that time period, though I wasn't the founder nor the sole contributor. I've done something like, I think, over 100,000 lines of code to it at this point. As the adoption of Rust in Python has grown, I've started thinking about not just being a developer on PyO3, but how to help build this ecosystem that's burgeoning. And so one of the activities I've taken on is I've begun to stream PyO3's development on Fridays on YouTube. And I've had a couple of breaks here and there for personal, family reasons or whatnot. But really, the intention is to be available on Friday mornings to show you what's going on. So if you're curious about that, please do come along. I should probably mention that's been Friday morning Europe time zone recently. So American friends, I might do some in the afternoons, and hopefully you can join then. Beyond that, I've been a part of Pydantic since it became a company a year ago. And I'm very pleased to let you know about our new platform that we're building, Pydantic Logfire. We're passionate about developer experience at Pydantic, right through from the open source package, which you might be familiar with, to PyO3, which I work on, not just at Pydantic, but in my own time too. And Pydantic Logfire is our take on how to make observability as good as it can be for a Python developer. So we're in open beta now. We have a booth downstairs. There's the URL. Please go try it and let us know what you think. Moving on to the matter at hand here, let's begin with that high-level overview. And a good question that I think we should start with is why Python and Rust? Well, there's lots of reasons that I've given to people over the years in different conversations. First off, it's that has worked. That's fun. Personally, for me, as I said, I love these two languages. I love writing code in Rust. I love writing code in Python. Why not mix the two? Furthermore, something that I praise Rust for again and again is its reliability. So in Python, you're probably familiar with Python exceptions, and these can surprise you out of nowhere and lead to exciting debugging sessions. Rust's take on error handling is slightly different. We have typically a structured result type, which you actually match on using pattern matching. So when errors might occur in your program, you have to actually handle them as part of the development experience. And so generally, it means when you deploy your Rust code, you know how it's going to run. And I find that a hugely satisfying experience. There is, of course, performance, which we hear about again and again as Pythonistas hearing about new Rust packages in the ecosystem, whether it be from tooling like Ruff, which Astral is producing so that we can all understand our code better, or whether it be Polars, the data frame library, which is increasingly competitive to pandas and is growing immense adoption very, very quickly. Security. if you've talked about with Seth Larson, Python Software Foundation developer in residence, he will probably have mentioned Rust to you as one of the options for Python's security story for the future. The point being that Rust's reliability forces you to think about many of these conditions, which in older languages like C and C++ would have led to problematic security vulnerabilities. Instead, in Rust, you can work with confidence that you're not going to create these same problems. And so outside of the Python ecosystem, it's the security advantage that is making large companies like Microsoft, Google, Meta, you name it, turn to Rust for their future development. Concurrency. Rust, on top of all these things, has a new take on concurrency that's very linked to its security story. It means that when you're writing multi-threaded code, you can do so with confidence that you're not going to produce data races. Some people describe Rust as like the concurrency panacea, and like it's not. It's still got its flaws. You can create a deadlock in Rust code just like you can in any other language that's got locks. In Python, you have threading.lock, and you might have experienced creating a lock, if you're using multiple locks, creating deadlocks, freezing your program. You can do that in Rust too, but you still get so many tools that help you work well with concurrency. And recently, Python 3.12 has brought sub-interpreters into the mix, and Python 3.13 is talking about a new experimental mode called free threading. And I'm really excited to see how Rust can help make both of these new ideas for Python a success. And finally, there's also a familiarity to Rust. It's got, sure, the power to go in and be a low-level language with all of these performance benefits, but actually it's taken quite a lot of ideas from the good things about Python. So syntax like for loops will feel familiar, and other bits of the syntax are borrowed as well. And so when I came along and discovered Rust for the first time, I already felt like I knew a little bit of that language due to my Python history. So that's a lot to take in. And I don't really think it's worth you trying to take away all of those in detail, but I want you to summarize it with this one line. Rust offers power and precision to go beyond Python's limits. And concisely what I mean by that is all of those ideas we've just talked about, when you need that little extra tweak that Python can't quite give you alone, that's when it's time to reach into Rust. And so what is PyO3? Well, PyO3 is a Rust project that gives bindings to Python. So you write Rust code when you're working in PyO3, but it's giving you that way to cross the bridge. And you can cross the bridge either way around. You can have Rust code running inside of a Python program, or you can have Python running inside of a Rust program. Today, as we explore these ideas further, we're going to be looking at the Rust code running inside of a Python program. And I think for a large part of the ecosystem, that's the dominant mode. But both ways around are equally prevalent or meaningful. We try hard to make it easy to get started with PyO3. So we have both a developer guide and we have the standard Rust documentation that many Rust libraries have. And it is a goal for us that many people are coming from Python to Rust for the first time when they're working with PyO3. So it's important that we try and hold your hand and guide you along. You can also browse our source code. It is open on GitHub, as you might expect. I think it's also worth mentioning a couple of supporting projects that will help signpost you as you're getting started. You might turn to a CLI tool called Maturin, which is used basically to set up your project in the right structure to get started. So newer tools like, I think Hatch has a command line mode to basically bootstrap your project, put in a pyproject.toml and a first file or whatever. And so Maturin can do the same thing for your mixed Python and Rust project. If you've got an existing project that you want to try adding some Rust to, you might alternatively look at Setup Tools Rust, which is a plugin for setup tools that gives you the opportunity to mix in Rust code to that too. And if you do a lot of matrix work, you might need to look at Rust NumPy, which gives you matrix NumPy interoperability. And why do I do this? Well, I believe that PyO3 should add Rust's power and precision to the Python ecosystem and everything that is already great about Python. I want there to be a low barrier to entry. Developers using PyO3 should be able to use what they know about Rust and what they know about Python to intuitively reach the result they want. And I want the interface between the two languages to be seamless. If you're a Python programmer and you're using a Rust library under the hood, I don't want you to necessarily know. I want it to just work like as if it were Python software. In the illustration I've provided here, I've kind of sketched that out. You might have 4 files, and maybe you swap b.py for a Rust implementation, and nobody needs to know. It just worked. That's my goal. I want to call out an explicit non-goal. I don't want to replace Python with Rust. I love both of these languages, and there's so much for the combination. Okay, so to now start getting a little bit more technical, let's try and illustrate how this actually is happening. Well, in Rust, we can declare a function using the fun keyword. I've named it here myRust function. And then what we can do is we use a thing called a procedural macro. If you're familiar with Python code, you can think of this like a decorator. It's something that will receive a function and can do some transformation with it to create a new function. And so, very much in that same way, PyO3, we have this PyFunction attribute, it's called in Rust. And we can mark that on top of our normal Rust function. By doing that, the attribute goes away and generates additional Rust code, which we target against Python's what's called CAPI, that knows how to go and create Python functions, Python classes, Python modules. And once we've got all of that code generated, the final step is to use one of these tools that we talked about, maturin or setup tools Rust, to compile that down into a place where Python can consume it. And this is a 3-step process, which is basically invisible for you. You write your Rust function, and you mark it, you run your compile, and it should just work. So, how does that consumption happen? Well, the magic lies in Python's import statement. You're probably familiar with using import statements to import other Python files. So, if you write the expression import b, then you'd think of it as going off and looking for a file b.py, which it would then load classes and functions from. Well, think about this a bit more. You already know that import b can also mean going to a folder and looking for an init.py and loading the same Python code from that file instead. But there's another mode. If the file happens to be correctly named native library, then the import statement can recognize that file name too and will attempt to load from it using what's called Python CABI, or Application Binding Interface. And so long as the native code contained in that file is structured in the correct way, then Python is able to import from it. And that native code is expected to go create Python classes, Python functions, and hand them out back to the Python interpreter so that you can interact with it, just like it were a module named b.py. And this isn't anything new. You've probably heard of C and C++ or Python in the Python ecosystem for a long, long time. Rust is using exactly the same trick. Okay, and so when I say Rust is using exactly the same trick, how much so? Well, I have to credit the methodology here to Seth Larson, who back maybe about 6 months ago did this analysis of understanding different languages uploaded to PyPI and what the growth of these languages is. And I reran the numbers recently, and what we have this graph here is for every month since around 2005, the number of different projects in that month that uploaded a certain language to PyPI. And we've just got 2 lines here. The blue line is C and C++, and the red line is Rust. And it's no surprise that the blue line extends out into the far history. And Rust first appeared on the scene somewhere around 2014, 2015. And so that's where the red line starts growing from. And the point we're at today is that every month, more than 350 different projects are uploading code to PyPI where their implementation is in Rust. And if you turn that around and count up roughly the number of times Rust code is downloaded to computers using Python across the world, we're looking at over 3 billion downloads a year. It's an absolutely staggering number, and I'm so thrilled by this. I also, when looking at these stats, couldn't help but notice a slightly interesting pattern here. So, looking just at the April numbers for the last 5 years, this is the number of projects that was uploaded in April 2020, April 2021, so forth, what I saw was that it looks like the Rust numbers are pretty much doubling every year. The C and C++ numbers, no surprise, are growing over that time too, because the whole Python ecosystem is growing. It's doubled over that same time frame. If, and this is a big if, those trends continue in the way they are, then there will be as much Rust as C and C++ in the Python ecosystem somewhere in the next 2 to 4 years. That I find truly amazing, and I'm really pleased by it. Let's now get a little bit more technical again. Here's a Python function. It's a little bit flawed. If you really wanted to pick this apart, it's very easy to. But what this function is trying to illustrate is the idea of counting the number of times you see a particular word in some text. And how it's implemented is that for some text, which we call contents, for example here, the Zen of Python, we proceed in to go line by line, and then word by word in that line. And if that word matches the thing we're looking for, suppose it was that word is, then we'll increment some counter and finally return that total. Now, if you take that and rewrite it using PyO3 as Rust code, you end up with this. And what I want you to take away from this is how similar it looks. We have the same kind of overall structure where we have a function definition. I already told you about the PyFunction attribute we need to place on the top to generate a Python function from this. The type hinting syntax is exactly the same idea as how Python does it. Sure, the types are a little different because Rust has its own unique take on a type system, but the same ideas are there. Rust is brace delimited rather than white space delimited, so we end up with a little bit of vertical growth because of that. But otherwise, even the iteration is the same. For line in contents.lines, for word in line.split. So if you are a Pythonista wanting to experiment with Rust for a first time to replace a hot loop, I really believe that this can feel accessible. And if you do this for this particular function, on this laptop here, I found that you end up with something that's somewhere between 2 and 4 times faster. Well, you might say that that's not really worth it for the amount of work that you had to go through to achieve that. But there's different takes on it. You know, that is a speed up that you got almost for free. If you're familiar with doing this for a few hot loops, it can suddenly add up. And also, you know, while we talk about performance, I also said it's about having that power and precision. What we've done here is we've taken a literal translation from one implementation to the other. Now that you've got that Rust implementation, you're free to go tune that further. And I'm sure if you wanted to, you could get this significantly better than 2 to 4x, but I leave that as an exercise for you. With our function ready, it's time to go down the rabbit hole. Okay, so we had our Rust function, called countercurrencies. And if we want to turn that into a real Python module to interact from, we need just a little bit more code than what I showed you before. We need to place it into a Python module in PyO3's nomenclature. So we do that with a mod, which is a Rust module, and we mark it with PyO3 PyModule. And this is enough to go and teach PyO3 that we want to generate the whole lot. The Python API that gets produced is exactly as you might expect. This module was called Hello PyO3, so with a little bit of boilerplate to actually set up the project, the thing that you'll eventually compile will import like that, Hello PyO3. We could assign a variable to contents, maybe A, B, C, D, 4 letters, split by whitespace, and then we could call that function, hello PyO3.countercurrencies, pass contents as a positional value, pass needle as a keyword value, with an argument A. And so this is really all we would need to do to call a Rust function. But the interesting question is, what does the interpreter do when we call it? Well, the Python standard library holds the first start of how we begin to answer this. There's a standard library module called dis. We can import dis and pass it to the function dis.dis, a string of Python source code, and ask it how it's going to try and interpret that. The response you get is a list of the bytecodes that the Python interpreter is going to attempt to evaluate to complete that instruction. And the important bit here is right at the end, we hit the call instruction. And that's where we're going to start. Now, I should note that I did this on Python 3.12. And the bytecodes really are an implementation detail of Python. So if you try this on other versions, you're likely to see a different output. And indeed, I think in Python 3.13, there's already been changes that mean that the call bytecode has been split out into multiple that are optimized for different pathways. So if you try and repeat this again in a year's time, you might see a slightly different result, but the idea behind it will be exactly the same. And so we'll start mapping out our rabbit hole here. We found the call bytecode. What does its implementation look like? Where are we going to go? Let's go there. I should say at this point, we're going to look at a few lines of C and a few lines of Rust. I know we've got an audience of Pythonistas here. You may know C, you may know Rust. That's not really the point. What I was finding as I was putting this talk together is that as I wanted to go on this journey, I found the source code was the best way to do it. And so I don't need you to read the source code, but I'm going to use it to illustrate the ideas. And so here, we'll start. In Python 3.12's source, you will find a file called bytecodes.c, which contains the implementation of call. And it's a fairly long instruction because there are a few different ways and special optimized cases. But eventually, you're going to reach this clause, which reaches for a function called pyObjectVectorCall. And it passes it 4 arguments: callable, which is going to be the function in question that we're trying to call, and then args, a value called positional args, ORed with some long flag that I'm not going to read, and keyword names. We'll worry about the actual values that are being passed around here in a moment, and we'll look at callable in some more detail, which controls where execution goes next. Before we move on, though, it tickled me when I was looking for this that the comment directly above the call to pyObjectVectorCall says callable is not a normal Python function. And I mean, it makes it sound like it's some sort of alien thing in the Python interpreter, but it's actually not that unnormal, because the Python standard library has a lot of functionality built in C. And all of the Python standard library functions, like sum, for example, will end up in exactly this place too. Okay, so we've said that callable controls where execution goes next. But what is callable? And in this case, I know that callable is a PyC function object. What is this? Well, again, the Python standard library has lots of core pieces that are implemented in C. So what we're looking at here is the definition of a PyC function object. And if you were to kind of think of this as a Python class, what you would see is the code class PyC function, colon, new line, and then you'd have double underscore slots, which you might have seen, and you would have 5 slots: mml, mself, mmodule, mweakreflist, vector call. If you're familiar with slots, the idea is that you're reserving some space to store a fixed number of attributes. And by this definition here, we're reserving 5 attributes internally in a C definition instead. And how does this PyC function object behave? Well, there's 2 things that are interesting in this. First off, the value mml. And that contains the definition of, it calls it in the comment a C function, but really it's any native function we want. And so in our case, PyO3 gave over some definition about the Rust function here. And additionally, there's a member at the end called vector call. And we already saw the name pyObjectVectorCall. It's probably not a huge surprise that this is containing the information to tell pyObjectVectorCall where to go next. But how does pyObjectVectorCall know to look there? There's one more piece to this particular bit of the puzzle. There is this thing called a type object. And this really isn't that alien either. This is the type object that is defining the type of PyC function. And in this definition of the type object, we have this thing that we call slots. Again, this is a slightly different concept. These are slots in the Python's C interpreter. And you can think of these, if you were defining a pure Python class, as like the double dunder attributes of your Python function, or Python type. So here, there's a couple that I want to pick out. The first one being this one built-in function or method. And this is what we call the slot name. And so if you were to import that function, hello PyO3.counterCurrencies, and ask for its type, the thing that gets printed back to you is class built-in function or method. And that's coming from right here in this definition of the type of PyC function. Another slot, which is interesting here, is the vector call slot, which is the one which is telling the Python interpreter where to look to go get that vector call resolved. And to give like a little bit of more illustration of what these slots are, you can think of them as when you're writing a Python class, you might have like a double underscore stir or a double underscore repr to define how the class gets printed, or double underscore add, so that if you wanted your class to add together with other objects, you define that behavior that way. When the Python interpreter is going ahead and building the final class or type object for your class, it's going to be putting it into slots in this very similar way, but rather than compiled in at the beginning, it's implemented at runtime. So now that we know where the vector call in direction comes from, we can kind of jump forward a little bit, and PyObject vector call, using that information, will end up here. This is a function called, well, C function vector call fast call keywords. It's one of the possible combinations of how the call can happen. I don't really want to go into what this function is doing. One of the most important ideas here, I think, is that it's preventing infinite recursion. And otherwise, the only line that we really need to look at is this one down here. And this is where we're calling into Rust. We have meth, which in this case is going to be a function pointer. And we're sending 4 arguments over. We're sending an argument that, with some long invocation of a macro, is basically you can think of as self. We're going to ignore that because we're looking at a function, not a method. And then there's 3 arguments, which again, we're going to keep seeing crop up. Args, nargs, and keyword names. We'll talk about those arguments later, but we've at least found where the hop begins. So let's go back to our map of the rabbit hole. Well, we started at that call bytecode. We looked into the implementation of it, and we found PyObject vector call being called. And with a little bit of a dance, PyObject vector call has to look in the type object of the function it's given and look at a slot to figure out where to go. Because the type is PyC function, which contains a function pointer to a Rust function, we'll end up crossing the line over to Rust. Where do we go in the Rust code? To answer that, we're going to go look again at our original source code we had for our Rust module. And I said that PyO3 generates code. Well, it generates a lot of code. We're going to look at a little bit of this. In fact, these sections that I've left highlighted are going to be relevant for us. We'll step through those a bit later in the talk. The one that we'll look at now is one of those. It's the top section, actually, and it looks like this. It's a function definition that PyO3 generated. It's marked as extern C fun. And this is important because it means that it's using the C ABI. And that means that if this Rust code is written with the right arguments, in the right structure, with the right return value, then when the Python interpreter has a pointer to this function and attempts to pass arguments to it using the C calling convention, then everything just kind of hangs together magically. And you end up with the result you want, where the 4 arguments make it across, and when the function is done, the return value goes back across. So there's a little bit more technical detail that you could go into there, but that's not really the topic we want to cover here. And instead, the interesting thing is more about the pathway. So what we've got here is this idea of what I've called a trampoline. And I think, strictly speaking, in computer science terms, trampoline wasn't the best choice of name, but it's still describing what I think is going on here, where Python has crossed over into the Rust code, and there's a little bit of work that PyO3 has to do before we can eventually make it to your function. What is that? Well, there's a couple of things that we need to think about before we go further. How do we make sure that that Rust and C boundary behaves correctly? There's 2 main things which PyO3 has to worry about when it's doing this. The first one is an additional mode of Rust error handling called a panic. What a panic is, if you've written an assertion in Python, assert 1 = 2, you would expect an assertion error to be raised by that statement. Now, in Rust, if you have an assertion that fails, the general assumption is that it's a developer bug which has gone wrong, and so you need to cleanly shut down your program. And it does this, called a panic. You can think of it a bit like an exception. It will basically go back up your function stack and close everything down. But the intention really isn't generally to stop it, unless you absolutely have to. Now, this is one of those cases where we absolutely have to stop it, because the Python interpreter is written in C. C++ has the idea of exceptions, but C doesn't. And in particular, the Python interpreter isn't built to handle these. So if a panic was to cross from Rust back into C, then basically we have an uncontrolled crash, which would be a complete disaster. We have to stop that. Second, I already spoke about how Rust is a multi-threaded language. And it's very straightforward in Rust to pass data around to another thread to dispatch work when you want to do things concurrently. That data that you can pass across might involve references to Python objects. Now, you've probably heard of the global interpreter lock. It's a protection built into CPython, which may change in the future, but the idea is that to protect against data races in the Python interpreter, you're only allowed to interact with Python objects if you hold the global interpreter lock. So, in the same way, if Rust is interacting with Python objects, it needs to hold that lock. Well, if Rust threads have done work, and they had a reference to a Python object, they didn't need to read it, but then they've done their work, and they're cleaning up, they could easily be throwing away references to these Python objects. And we're not allowed to even throw away references without holding the lock. So we could try and acquire the lock. There's a good risk that we might produce deadlocks if we did that automatically. So PyO3's alternative strategy is to defer that work for another time when we know it's safe to do so. We defer that reference count operation until we can. And a good time to do it is when we're entering PyO3's framework again from a function call. So we'll do that here. And so this is what the implementation of that trampoline looks like in PyO3. And it's got those pieces that we just spoke about. First, we established the boundary so that the panic can't cross out back into the Python interpreter. And there's two defenses that we place. We lay this thing called a panic trap. And it works a bit like, it behaves like a context manager in Python. So if this were Python code, you would do with panic trap as trap, and then indent everything. But in the same way, when we exit this scope, the trap will exit. Except we call trap.disarm a little bit lower down, and then it's all okay again. And the idea is that if a panic were to ever cross inside that space between trap and trap.disarm, then we would abort the program to never allow that crossing into the Python interpreter. Now, an abort is not great, so there's a second option, which is to catch the panic. And this is a standard library function built into Rust, so that when that error is propagating over and up towards Python, we instead can turn it into a Python base exception and keep it going. And this is a little unpleasant, sure, because then when you get back to your Python code, suddenly you've got a base exception flying up to the top. And if you've ever done stuff, generally the rule is don't inherit from base exception because you'll never catch it. And it happens in this case that we kind of don't want you to catch it. We want to shut down. Something has gone wrong. An invariant has been broken. But still, with these defenses in place, then at least things can close cleanly. Second, as we said, there's a call directly into PyO3's framework to update some deferred reference counts, if there are any. Hopefully, the common case is there are none of these, but it's essential that we get things right, so this framework call might well be there. And then finally, down here, we can move on and do the real work. Let's just recap again. We've gone down the rabbit hole. We started with the call bytecode. We looked at the implementation of it and found PyObjectVectorCall. After a little bit of resolving, that crosses over through a function pointer into Rust. And in Rust, we arrive at this trampoline, which is setting up some critical safety invariants for us. We establish a boundary, and we update some deferred reference counts. What happens next? Well, I'm sorry to say it's still more generated code, and it's this rather long piece of generated code on the right. But it's looking a lot closer to our actual function now. In this case, PyO3 has called the generated code a function called pyfunction countoccurrences. And it's still taking those arguments, args and args, and keyword names. And it's returning a result, which is again hinting, like I said back at the beginning, to Rust's error handling, where it's done by structural pattern matching rather than by exceptions. And what does this function do? Well, the first thing it's going to do is finally handle these arguments. So let's talk a little bit about what these arguments are. These arguments come, you've seen this name a few times already, from the fast call calling convention. Let's remember what we did. We took our function, we sent one positional argument in, called contents, and then we also passed a keyword in for a needle equals A. And so we had three values there, args, nargs, and keyword names. And what ends up being structured is args is a C array of Python references. So a continuous memory block, and it's just a pointer to the beginning of that block so that we know where to read from. Then nargs is 1. It's the number of positional arguments. And finally, keyword names is a tuple, a Python tuple, as a reference passed in. In this case, that Python tuple contains one value, which is needle, because we passed needle position keyword by keyword. And so, because the tuple is also of length 1, that's how we get to the total length of our C array of 2. Now, PyO3 has code inside its framework to go from this representation of these three values to a set of Python objects that, again, represent the function call. We have all the information there that we need. And that's what the next bit of the function does. We set up in PyO3's nomenclature a function description, which knows which arguments are keyword only, how many have required values, and then sets up the space to save those, in this case, 2 values in a variable called output. And then finally, we use a PyO3 internal call, extract arguments fast call, to do that work. If you sent, say, 3 positional values or keyword argument names that were irrelevant, then PyO3 tries really hard to give you exactly the same error message as you would receive if you called a normal Python function with an invalid argument. Once we've got these, they're still Python objects. In this value output, we'll have the 2 Python references to the contents and the needle. And so there's a final step. And I felt like we weren't best served by going through this final step in too great detail, but we can go from each of those 2 Python objects to corresponding Rust values. And just to give you a brief illustration of what happens, Rust has this idea of things called traits. Traits encode behavior. They're somewhere along the lines of something like a protocol or an ABC in Python terminology. And so for every corresponding Rust argument type that you might choose, PyO3 implements a trait that knows how to convert Python objects to it, or fail. So in this case, both contents and needle are strings. And so PyO3 would be expecting you to pass 2 Python strings, and knows how to map those into Rust string values for you. So then, with that done, it's this piece here, which is finally making that function call. And we found our way to the bottom of the rabbit hole. To recap, we looked at the call bytecode. From the implementation, we found PyObject vector call, which eventually stepped through a function pointer into PyO3's Trampoline, which set up important safety invariants for us. With those in place, we got on with the argument passing of the fast call arguments. And then the final step was to make a fairly trivial looking function call right at the end. Let's wrap up. There are 3 main things that I want you to take away from what I've said today. The first one is that repeat idea. Rust offers power and precision to go beyond Python's limits, and I want it to be able to add to what's already so great about the Python ecosystem. Loading Rust code, as I illustrated, is just an import. If you were to try and follow an import down the same kind of rabbit hole, it would look very, very similar to the kind of thing that we just did. It really is another set of function pointers that cross over into native code in the same way. And then finally, we looked at a Python function call and how it ended up executing Rust code, in reality, in just a few steps. Thank you for listening.
So we have a few minutes for questions. If anyone has a question, should be a mic out there somewhere.
So you mentioned a little bit about how Rust might become particularly powerful as more options for concurrency are unlocked in future versions of Python. I was curious if you've put some additional thought into how we might be able to reconcile the memory model that Rust expects with what Python exposes. So I think, in general, like I'm trying to imagine the future, and I'm just seeing lots of mutexes around Rust objects, and then interoperability between native extensions becomes a little bit harder without some other adjustments to things like the buffer protocol. And so I was curious if you had thoughts, or if you're familiar with any work that's happening there to make it easier for extensions implemented in Rust to interoperate with the rest of the native extension ecosystem.
Yeah, it's a great question. So I guess the thinking here, for those of you who aren't super familiar with the Rust memory model, is that it doesn't allow you to have multiple threads editing data at the same time. So if you have the ability to mutate data, you uniquely are only able to access that. And so in this future where, well, that's what creates a great multi-threading story for Rust, because it avoids the potential of creating data races. And you mentioned in your question mutexes. Mutexes is one of those ways that you actually can modify data from multiple threads. A mutex is a lock. So when one thread holds that lock, it can safely modify the data, in Rust's case, contained by the mutex. And so, yeah, it's an excellent question. How do we reconcile the fact that Rust doesn't want you to modify stuff with the fact that we're going to have a multi-threaded, potentially Python world where stuff can be modified all the time? So there's really like two different things that we can look at here. So the sub-interpreters, which already exist, are enforcing isolation as the way to protect against this. Each sub-interpreter has a separate set of Python objects, and the rule is that they can't cross between interpreters. And there's advanced work going on. I think Yuri spoke about it in a talk earlier today to begin to explore possibilities of how some can be shared. But really, isolation is the protection there, and that will avoid the need for locking. Now, the alternative, the free threading, is, yeah, it's a very interesting one. I think, in general, Rust leans into that model very, very well because it's how it already wants to think about the world. But you're right that the naive implementation, basically every PyO3 object contains a mutex, and we lock them before we do anything. It's something that's been playing around on my mind. I think there are different ways that we can look at this, such as enforcing that, at the moment, you already have that constraint, but you're also held by the GIL, which protects you from achieving that frequently. So the same problem already exists, and maybe we can modify things so that you might still find that you either block or you have an exception if you try and modify things concurrently. But also one thing, again, is the fact that Rust doesn't like you modifying data. And so helping build data structures which basically lean into that immutability is something that I want to encourage from PyO3 extensions as well. At the moment, PyObjects or Python classes implemented from Rust give you mutability as a choice for free. And I think in the future, that might be a more deliberate opt-in. So you start with your class being immutable, and if you're prepared to go for the complexity of locking or other exclusion mechanisms, then you'd have to opt in. And I think that helps solve a lot of the problem.
I think we're sort of out of time at this point. Perhaps if anyone else has a question, you can catch David outside. Otherwise, let's have a big round of applause for the wonderful talk.
Thanks very much.